I'm Johnny Hartung.
I'm Brendan Waldman.
And I'm Peter.
And I'm Jack Taylor.
And we are the Cascaders!
We are here today to explain forces, waves, energy, and weathering and erosion of the Cascade Range.
The Cascade area lies on the convergent boundary of the North America and Juan de Fuca plates. Under the Juan de Fuca plate is the Pacific plate, which forms a transformed boundary with the Juan de Fuca plate.
As the stress builds up between the plates, it gives the excess amount of pressure causing strain, which leads to the formation of mountains, volcanoes, major earthquakes. To help explain these facts, we'll perform a series of experiments.
Between the Pacific and North American plate, there lays a subduction zone. Also, when the Juan de Fuca and North American plates converge, the Juan de Fuca plate subducts under the North American plate. This means that it is older than the North American plate.
Whoa, hey there, sorry. I just want to explain to you guys that with a lot of plate boundaries active, there's a lot of forces involved.
This example right here is like the Skagit River flowing into Diablo Lake. The river wants to stay in motion unless acted upon by an unbalanced force, which in this case is Diablo Lake.
This is the North American plate, and this is the Juan de Fuca plate.
This here is an example of the North American plate and the Juan de Fuca plate colliding. This is explained by Newton's second law, that when an object has greater mass, there is greater force.
This is North American plate, this is the Juan de Fuca plate. Subduction. The Juan de Fuca subducts under the North American plate.
Again, this shows the Juan de Fuca and North American plate following Newton's third law. And to help us with this, we have Elmo from Sesame Street. Elmo, how are you doing?
I'm doing great.
Elmo, can you explain this?
Well, this states that every action has an equal and opposite reaction. That's Newton's third law. The opposite reaction is portrayed by one plate sliding above the other, facing the bottom plate to go down.
Oh, thank you very much, Elmo. You've been a great help.
Oh, well, it's glad to be here.
Rivers create high forces on objects they come in contact with because of their high velocity. Newton's second law is shown because since the river has a high acceleration/velocity, it creates a large force to carry the sediment. And Newton's law states that force equals mass times acceleration.
Force!
This is the Juan de Fuca plate, and this is Pacific plate.
Earthquake!
This is an example of the Juan de Fuca and Pacific plate at a transformed boundary. The plates slide past each other and create friction because they rub together, and friction creates earthquakes.
Now we will show you how waves influence the Cascade Mountains.
P wave. S wave. L wave.
This is an example of the many earthquakes occurring before the Mount St. Helens eruption. As you can see, the L wave is the most destructive wave because it moves up and down and side to side.
P wave.
S wave!
L wave!
The three runners in the race show the difference in arrival times of the three different waves when they arrived during one of the pre-Mount St. Helens earthquakes in the Cascade Range. P waves reach the location first, next are the S waves, and then the L waves come at the end.
During earthquakes in the Cascades, sediment is knocked into lakes. As the pebble is dropped into this experiment, it creates a wave, which is shown by the ripples in the water. This transverse wave is carrying the energy away from the original splash.
Earthquake! Oh my God!
As Mount St. Helens erupted, a longitudinal wave, or a sound wave, was spread out through the air.
Boom!
Before Mount St. Helens, many small earthquakes occurred. These seismographs revealed that these earthquakes were produced by small waves. This can be determined by looking at the amplitude size. The smaller the amplitude, the smaller the wave.
Energy also has a big role in the Cascade Mountains.
The pipe here represents a mountain and the water in the Little Nisqually River, which starts at the top of a mountain. The river has its highest potential energy at the top of the mountain, as seen here. The height determines the potential energy, and the water is at the highest point here on the pipe.
Potential energy. In 1865, Mount Hood blew its top due to an immense amount of pressure. The bottle portrays Mount Hood in a case of Diet Coke and Mentos reaction, represents the magma and the gas reacting. All this pressure shows potential energy, which is then transferred into kinetic energy as it erupts. The dam transfers to light energy.
The replica dam that was just shown is an example of the Diablo Dam flowing into the Steeken River. It shows that kinetic energy can be transferred into light energy, because energy isn't created nor destroyed, it's only transferred or transformed.
The Juan de Fuca and Pacific plates build up a lot of potential energy as they grind past each other. Stress holds them back, but gives them the potential to go in motion and cause an earthquake.
Juan de Fuca plate, Pacific plate. Stress lets out. This is volcanic ash.
For science!
Red, you got me!
The ash plum has its highest potential energy once it reaches its peak in height, because height determines potential energy once the plum starts to drop. All of its potential energy is slowly converted into kinetic energy.
I think he's done.
The Cascade Range, along with this activity, has tons of weathering and erosion.
With multiple rivers in this region, there is a lot of erosion because rivers carry heavy particles in the bed load and light particles in the suspended load, and it erodes them away to different locations.
Also, there is weathering associated with rivers because they have a high kinetic energy going past the cut bank, and that energy weathers away at it.
Exfoliation occurs when such things as Mount St. Helens erupts and its side broke out. Less pressure on the mountains causes the layers to peel.
Exfoliation also occurs when glaciers melt, causing less pressure and layers to peel.
When volcanoes erupt in the area, rocks break down and erode down the mountain. Also, the ash plume is eroded away to a different place by the wind.
Lastly, during eruption and earthquakes, abrasion occurs because rocks smash into other rocks, which weathers them apart.
As you can see, there are many examples of forces, energy, waves, and weathering and erosion associated with the Cascade Range.
We're the Cascaders, and thanks for watching our presentation.